We have successfully covered algorithms like Dijkstra's, Huffman coding, and the fractional knapsack. Those methods rely on the greedy strategy, which works by making a single optimal choice at every step. But solving complex, multi-path logic puzzles requires a strategy that can account for failure. Take a look at this two-dimensional maze. If an agent relies on the greedy method, it selects the path that looks best in the moment. When it hits a solid wall, it freezes. The limitation of a greedy algorithm is that its choices are permanent. It lacks the logic to revisit a previous decision. Backtracking provides a way forward by allowing an algorithm to move backward. Instead of permanently accepting its first decision, it tries a choice, checks if it leads to a valid state, and if that path fails, it returns to the last intersection to try an alternative. To solve puzzles with hundreds of branches, an algorithm must be able to recognize when it has hit a dead end and deliberately undo its own previous moves. This process relies on a four-step logic loop. You try a choice, check its validity, go back if it is wrong, and then try another path. Imagine you forgot the 4-digit passcode to your phone. You have a massive set of potential numeric combinations to test. You type in 1, 2, 3, 4. The phone rejects it. You clear the entry, go back to a blank slate, and try 2, 5, 8, 0. When that fails, you clear it again and try the next sequence. This sequential trial process is highly efficient because it ignores doomed paths early. If you know the code definitely does not start with a 9, you stop entering digits the second you type a 9. You don't waste time finishing the remaining 3 numbers in that sequence. Backtracking functions through the systematic, ruthless elimination of incorrect paths as early as the constraints allow. Look at this digital combination lock, displaying a partial entry of 1, 2. In computer science, we define this snapshot of a partial solution as a state. Every time the algorithm makes a decision and fills the next slot, it transitions into a new state. To organize every condition an algorithm encounters, we use a state space. This is the set of every possible state that can exist for a problem. For a 4-digit PIN, this space includes all 10,000 combinations from 0000 to 9999. The goal of a backtracking algorithm is to navigate this state space efficiently, finding the correct answer without needing to check every single individual lock. To search the state space predictably, algorithms map out choices using a branching structure called a state space tree. It begins with an empty initial state at the top. As the problem progresses, the tree branches out geometrically. Every new branch represents a different choice, and every connected node represents the resulting state of that decision. The algorithm explores by moving deep down one specific branch. It continues downward until it solves the puzzle, or until it hits a constraint proving the current state is invalid. When it hits a dead end, the algorithm backtracks. It abandons the failed node, retracts its path up one tunnel to the parent node, and flows down the immediate neighbor branch to explore the next option. Modeling a problem as a state space tree transforms a chaotic trial and error process into a rigorous mathematical search. This process relies on a general method for problem solving. First, start from an empty solution. Next, choose one possible option. Then, check if it is valid. If valid, the algorithm continues deeper. If invalid, it undoes that move and tries the next available option. The technical challenge is how to program a system to execute this branching and undoing while keeping track of which branches it has already explored. This is why almost all backtracking algorithms utilize a recursive strategy. Recursion is ideal here because once you make a single choice, like placing one piece on a chessboard, the remaining task is simply solving the exact same problem with a smaller input. Moving deeper down the state space tree is programmed by calling a recursive function. Reversing course and moving back up the tree is accomplished simply by hitting a return statement. The inherent memory stack of a recursive function naturally preserves the history of the states. This stack allows for the effortless reversal of bad decisions and ensures the algorithm never re-explores a failed branch. Choosing between these two approaches is a trade-off between execution speed and mathematical thoroughness. The greedy approach is fast. It makes permanent decisions based on the immediate local option, never returning to previous states. Backtracking operates differently. It relies on continuous trial and error, making reversible decisions to conduct an exhaustive search across multiple possibilities. Greedy algorithms sacrifice exhaustive accuracy to gain processing speed. Backtracking sacrifices that speed to guarantee it will find a correct solution if one actually exists in the state space. Because of its thoroughness, backtracking is required for complex constraint satisfaction problems. It's the logic behind Sudoku solvers, graph coloring assignments, complex Hamiltonian cycles, and automated maze solving. However, there is a performance cost. Because backtracking maps out so many branching possibilities, the computation time grows exponentially as the problem size increases. This makes it very slow for massive, unconstrained datasets. Additionally, the deep, nested recursive function calls required for this method create significant memory overhead for the computer's call stack. Despite these time and memory costs, backtracking remains a vital tool. For highly constrained logic puzzles, it is often the only way to find a valid solution. For exams, remember the acronym CCBTS. Choose your path, check validity, backtrack on failure, try again, and secure the solution. Remember that unlike standard greedy methods, backtracking will systematically explore multiple routes until the final condition is met. In our next lesson, we will apply this entire theoretical framework to one of the most famous challenges in computer science, the n-queen problem. Understanding the movement of a state space tree is the foundational skill for mastering complex algorithm design.